All right, to wrap up here on reciprocal space, I want to mention some other kind of important points about this. All right, so first of all, any real space crystal lattice has a unique corresponding reciprocal space lattice. So if I can think of a real space lattice, then I can make a reciprocal space lattice out of it, right? I hope that was obvious at this point, but I just wanted to make sure. Also, each reciprocal space lattice point represents a set of planes HKL. So it's important to kind of think of this not necessarily just one plane, but a set of planes HKL in real space. All right. Lastly, we showed this, but DHKL star, that vector, is always normal to the plane HKL in real space. All right. Also, the A star vector is normal to B and C. And so I'll show you this here in a slide. All right, I just mentioned that the A star vector is always normal to the B and C vectors in real space. And so this figure in your textbook, figure 2.8, does a good job of sort of illustrating that. So if we look at A star here, and that's part of A, B, and C star in reciprocal space, if we draw those in comparison to A, B, and C in real space, you'll see that this A star vector is normal to the B and the C vector, right? So you can do that for any combination, right? So if I'm looking at the C star, then that's going to be normal to A and B, right? And that goes back to the definition of the reciprocal lattice vectors with the cross products, right? Because for C star, you're looking at A cross B, A star, you're looking at B cross C. And so that's kind of back to that definition. But this, I believe this does a pretty good job of kind of visually showing you what that's referring to. All right, the next point I want to make is related to a point that's made in the book. So in the book, it says that the A vector times the the A vector times the A star vector is equal to 1. So this is an error. It should say A vector dot A star equal 1. So it's a minor point, but you want to make sure that that's referring to the dot product since we're talking about vectors here. So that's just a clarification of the book. So the A vector dot the A star vector is equal to 1. All right. So a couple last points here. In general, the A star vector is not parallel to the A vector. So this is only the case if the crystal system is orthogonal. So things like the cubic, then they are parallel, but that's, again, not the case for all crystal systems. All right, and the last point I want to make is that planes in a zone form one reciprocal lattice plane. All right, so we haven't talked about what this zone is referring to, so let's go into what we're talking about when we talk about planes in a zone form one reciprocal lattice plane. All right, so when we're talking about planes of a zone, what this means is that these planes in a zone share a common direction. And so all of these planes share a common direction, and that direction is all one line. So they're all parallel to one line. And so that's what the zone is. It's basically that common direction. So let me show you it in the slides. All right, so this is the illustration of planes of a zone. So take the three planes that I have shown here, the 1, 1, 0, the 0, 1, 0, and the 1, 0, 0. If you draw out these planes, what you find is that they all have a given direction on the plane. So if I look at the 1, 1, 0 plane, I can draw the 0, 0, 1 direction within that plane. And the same thing for the other two directions. So they all share the 0, 0, 1 direction. And so that is my zone, sometimes referred to as a zone axis. And so that's important because when we're looking at one of these reciprocal lattice diffraction patterns, that zone is the direction of the beam, right? So we can basically determine the zone axis because that is the axis that the beam of light or electrons is arranged and to create this pattern of different planes. So I align my system such that my beam is aligned with the zone axis because only planes that contain that direction will show up. And so that's important to mention. So this common direction is known as the zone axis. All right, so like I just mentioned, that common direction or line in the zone, what we're talking about with the planes of a zone, that common direction is known as the zone axis. So we'll come back to this a lot when we talk about diffraction. And so what we see is that planes in planes of a zone don't necessarily have the same indices, right? So you saw in that example we had a number of different types. So we had 1, 1, 0, we had 1, 0, or sorry, 0, 1, 0. So they don't necessarily have the same indices, but they do share common direction. All right, and so we can formalize this using the dot product. So if we have a zone axis and we define that as a direction, so it's going to be u, v, w, and we look at any plane h, k, l, if it belongs to the zone, it has to follow what we call the Weiss Zone Law. And that is basically the dot product. So it has to satisfy the dot product between the axis and the plane, which is h times u plus k times v plus l times w equals 0. So a note here, again, this is the dot product. So this is the dot product between the direction and the normal to the plane. and that's why it's 0. So the direction and then plane are normal, so 90 degrees apart, and so the direction is coplanar to the plane listed. So that's kind of where this Weiss zone law originates from. All right, so for the next quiz question, I want you to pause the video here, and what you're going to do is you're going to come up with the Miller indices of at least one plane that has the direction or line 110 as its zone axis. So you're going to come up with a plane that satisfies the zone axis of 110. So pause the video, see if you can work that out, and come back and we will go over the answer. All right, so now you've answered the quiz question. Again, we're trying to find the Miller indices of at least one plane that has the line or direction 110 as its zone axis. And so any plane that satisfies the following relationship. All right, so we start with the Weiss zone Weiss zone law, which is this. And we know that our direction, u and v, are both 1. So we have, we can substitute in 1 for u. That just leaves us with h. 1 for k. That just leaves us with v. And then 0 for w. So that means that those two, h and k, u and v are both 1. W is 0. So that leaves us with h plus k equals 0. So that leaves us with h has to be minus k. So basically any plane that satisfies this condition. So let's say that I pick an h of 1. So I know right off the bat that my first Miller indice is going to be 1. That means that I have to have a negative 1, right? And then any value of L is acceptable. So it could be 0, 1, 2, 3, 4, it doesn't matter, right? So this plane would satisfy, but anything that satisfies this relationship would work.